Welcome to ChemVid. Today we're going to be talking about ionic versus metallic bonds. However, we're going to mainly stick with just ionic bonds and how we know how strong they are. Okay? So in order to do this, you need to get out your ionic and metallic bond notes. And we are going to look at the main properties of ionic compounds. So the first thing we need to review is the cubic structure. So if you recall, every ionic bond is going to have a cubic structure, meaning that because the cation and the anions come together in alternating order like this, they always form some type of cube. It's called a lattice structure. Okay? Remember that any ion that is negative will be bigger than the positive ions because they have gained an electron. Okay? So if I wanted to draw KBr, potassium bromide, first thing I need to do is I need to identify the cation and the anion. Since potassium is the metal, I know that this guy is going to be positive. And since bromine is a nonmetal, I know that he's going to be negative. All right? So every ionic compound has the same structure. You do positive, negative, positive, negative, positive, negative, positive, negative. Then I just need to label positive, negative, because that way I know what's going on. And then I need to write my key. Potassium is the positive cation. Bromine is the negative anion. Bromine's bigger, potassium smaller. That's how you draw it. Okay? Alright, the next thing we need to talk about is lattice energy. So lattice energy is the energy it takes in order to take apart one of those lattice structures. So if I look at this lattice structure, I know that the cation and the anion are attracted to one another, and that's what keeps an ionic compound together. So the lattice energy is the amount of energy it takes to pull those ions apart from each other. Okay, so it's the amount of energy it takes to separate them. And that energy depends on two things: size and charge. So the smaller the ion, the greater the attraction. And the bigger the difference in charge, the greater the attraction. Go ahead and write that down. Alright, so smaller, greater attraction. So over here to the side, I want you to draw a little picture. When you think smaller, think about little toddlers. Oops, don't have my brush. There we go. Toddlers can hug each other. And because they're so small, they can grab each other and they can stay really close, all right? So you can think of it as when they hug each other, they can hug each other and get their arms around each other, show them love. Or you can think about when they're fighting each other and the mom comes and starts yelling at them and trying to pull them apart from each other. And because they're so little, they have a really good grasp on each other, so it's hard to pull them apart, all right? So toddlers, because they're so small, they can really hold on tight. For, let's say we have a sumo wrestler, okay? Sumo wrestlers are very large. Okay? And so when a sumo wrestler tries to grab one another, unfortunately, they are so big that it's really hard to hold on to one another. So because they're so big, they're kind of trying to grab each other and, get their arms around each other, but it's pretty difficult. So it's easier to separate sumo wrestlers rather than it is to separate my little toddlers. So remember, smaller is harder to separate than bigger, okay? Just like your sumo wrestlers. Okay, so the next thing that determines how hard it is to pull apart a ionic compound is the charge. So think about the charge as a magnet. If I have a positive and a negative magnet, they stay together pretty well. But let's say I have a stronger magnet, like 3 times stronger. And I have a stronger anion magnet. Okay? These two, the ones with the stronger charges, or the bigger difference in charge, are going to be harder to pull apart because they're stronger magnets. They have more what we call electrostatic ability to pull. All right? So as I look at a bigger difference, the bigger the difference in charge, the stronger it is because they are stronger magnets. So how do we apply this? Let's go ahead and try our practice problems. Okay, so if I wanted to know who has the greatest lattice energy, the first thing I need to look at is size or charge. I like to look at the charge first because it's the easiest. Now you can do it either way, I just choose the charge first. So I look at my periodic table and I know that sodium is in the first column. So that means it has a +1 charge. Chlorine is over here in group 17, which means he has a -1 charge. So the difference between that charge is 2. That little triangle, all that means is difference. Okay? So if I was to look at a number line, I have a 1, and then I have a -1. See how there's 2 spaces in between there? That's what my delta charge is. So my delta charge just tells me the difference in charge. All right, potassium. Potassium is also in group 1. So I'm going to do a +1. Chlorine is a -1. Calcium, however, is in group 2. So he has a +2. Chlorine still has a -1. Now you may be saying, well, there are 2 chlorines, so wouldn't that be a -2 charge? No. Whenever we are doing lattice energy, we only do 1-to-1 ratio between our ions. So we're only paying attention to how hard it is to remove 1 calcium and 1 chloride atom or ion from each other, not the entire package, okay? So you only have a -1 charge. All right, so now that I have this, my delta charge, 1, 1, I'm going to add up the absolute values, and that gives me my delta charge. 2 and 1, that's a delta charge of 3. Okay, so from looking for my delta charges, who's going to be the most attractive? If you said calcium chloride, you are correct, because calcium chloride has the bigger difference in charge. So this guy is the most attractive. Most. However, potassium chloride and sodium chloride have the same difference in charge, so I need to go to my second candidate, which is size, in order to tell the difference apart. Okay? So I'm going to look at the periodic table. Since both of them have chlorines, chlorine doesn't matter, they have the same size. So I'm just going to look at the metals and compare sodium and potassium. Since sodium is higher up on the periodic table, that means that sodium is smaller, correct? So if sodium is the smaller one, and smaller means more attraction, that means that sodium chloride is the next attractive, and potassium chloride is the least attractive. So again, whenever you're doing ionic strength or lattice energy, you first need to tell their charges, find their delta charge. If they have the same delta charge, look at their size, and you can tell between who is the smallest and who is the biggest. All right? Now, I want you to pause the video, and I want you to try doing potassium iodide, potassium fluoride, and strontium chloride. Tell me who's the most, tell me who's the least, and who's in the middle. If you haven't tried it, try it before you watch the answer. Okay, so First thing I do is I find their charges. Iodine is a -1, potassium is a +1, so that's a delta charge of 2. Fluorine is a -1, potassium is a +1, so that's a change of 2. Strontium is a +2, chlorine is a -1, so that's a delta charge of 3, which means that strontium chloride is my most attractive. Why? Because he has the greatest delta charge. Then I look over here, oh, these guys have the same charge, so I look at the size. Potassiums have the same size, so I'm not going to worry about this. Fluorine, if I look on my periodic table, is smaller than iodine, so fluorine is going to be the next attractive, and potassium iodide is going to be the least. Now what I want you to try to do is I want you to look at all of these guys, and I want you to put them in order of smallest to largest attractiveness, okay? So your most attractive is going to go over here. Follow the steps. First, look at all of their charges. Next, look at their sizes if they have the same charge, okay? So that's your homework. Okay, so your homework is to finish problem number 1. Put these guys in order. Again, remember charge then size. And we will go over the rest of the notes in class next time. Good luck!